All right, so as you saw in that outline, we are working through lesson 2-8. It kind of gives you the outline of what we're going to learn and when. So as part of the warm-up, I have you solving inequalities and graphing them. This is what we did in chapter 1. So go ahead and take a minute and look at 1 through 6. Remember that absolute values are split into the positive and a negative. So 4 and 5, you should have 2 answers. And 6, you have to remember great 4 less than. Uh, 6 shading either opposite or together. Yeah, together. So I know like 5, 6, and 7, or 4, 5, 6 might be a little difficult, but all of us are supposed to be able to do 1, 2, and 3. All right. So for number 1, you had p less than or equal to 5/4. This is a less than or equal to, therefore it is a closed circle and shade to the left. Number 2, t is greater than 13. Okay. Open circle, shade to the right. And then in number 3, you have that t is less than or equal to -3. So once again, closed circle because it's less than or equal to, shade to the left. So we focus a lot on open or closed circles. In 4, 5, and 6, I told you those are absolute values. So absolute values, when we solve, those are kind of like the equivalents of my intercepts. So you have -4 and 4 in number 4, because you have to set 4c equal to +18 and -18. all absolute values have two solutions. And then in 6, it's an absolute value inequality. So much like 1, 2, and 3, you have many solutions. The absolute value is great or. So or means that it can be either h greater than or equal to 3.5 or h less than or equal to negative 3.5. The reason we start lesson 2.8 by solving inequalities and reviewing linear functions over break is because we're going to take those two ideas and sort of smack them together to look at graphing linear inequalities, which means we are going to graph lines with shading and multiple solutions. Okay. So what I want to do to start is to graph each of those points as well as the line. So you're going to graph the line as well as plot each of those points. So the line is y equals 2x plus 3. That means that this graph has a y-intercept of positive 3. So you're going to plot your point at 0, 3. The 2 represents the slope. So that tells you the graph goes up 2 and over 1 from my y-intercept. It can also go down 2 and left 1. And then what we're going to do is plot each of those points on the graph. So you're going to plot the point negative 2, negative 3. You're going to plot the point negative 2, negative 1, negative 1, negative 1, and so on and so forth. Yep. Hurry up. From now on, you need to go before the lesson or after the lesson. Okay. As you work your way through each of those points, what you will notice or start to notice is some of those points are above, below, and on the line. So what we want to do is talk about what those points are and what they represent. So I have color-coded mine so you can make sure you graph them correctly. So the first point is below, the second point is on, the third point was below, then the next 4 points were above, then below, and then on. Why do I care about if the points are above, below, and on? Because those points are going to represent solutions or non-solutions. So as we graph linear inequalities, we're looking for the solution set. So it says, are all of the points that satisfy the inequality y greater than 2x plus 3 above, below, or on? So what you do is pick a point that is above, pick a point that is below, and pick a point that is on the line, and determine if it makes the equation true or not. So a point that is above is like 0, 4. So 0 is x, y is 4. So that's like 4 greater than 2 times 0 plus 3. A point below the line is -2, -3. So that's -3 greater than 2, -2 plus 3. And on the line is -2, -1, or you have 7, 0. It doesn't matter. You could pick either one. Let's do 7 and 2. So you have 7, 2 times 2 plus 3. So on, below, above. And what you would want to do is simplify each of those. So here we get 4 is greater than 3. Here you get -3 is greater, well, 2 times -2 is -4. -4 plus 1 is -1. And then here you get 7. 2 times 2 is 4. 4 plus 3 is 7. Is 4 greater than 3? Yeah. So this is true. So it says, are all the points that satisfy the inequality above, below, or on? Well, the points above are true. So I'm going to say that above satisfies. Below. Is -3 greater than -1? No, so that's false. So that does not satisfy my equation. Is 7 greater than 7? No, so that is also false and does not satisfy. So the points above the line satisfy the inequality. So what we're going to do is talk about shading and satisfying. So being true or false and as part of our solution. There we go. All right. So an inequality is expressed as y less than mx plus b, where just like in the past, m represents my slope, y represents, or b represents the y-intercept. So if you have the inequality or equation y equals x, which is known as the parent function, my slope is 1, and my y-intercept is 0. Because the board is challenging to write on, I'm going to leave some of this up while I kind of scroll back and forth so that when we talk about it, you can start to write it down. So I'm going to take that away, but I promise I will bring it back. All right. So now we want to work our way through the example. It says you have the inequality given y less than x. And we want to compare it to the line y equals x. So y equals x is just a normal linear function, right? And every x that is a solution would be equal to y. Where the solutions to y less than x are going to happen below the graph. So this graph right here in green represents y equals x. This is our main line we are talking about for now. So you can go ahead, plot the graph y equals x. That means your y-intercept is 0, your slope is 1. So that means it goes up 1, right 1, up 1, right 1, down 1, left 1, down 1, left 1. That is the line we are talking about for all of these problems. if I gave you the graph y less than x, so you don't have to shade, I'm just going to shade up here. That would be like shading below the line. So how does the green line and shading below that line, how are they different? What could you say is different? Well, the difference is coming from where the solutions are. The solutions for y less than x are all the shaded blue points below y equals x. The solutions to y less than x would be all the shaded blue points less than y equals x. If the graph was y less than or equal to x, now it would be all the blue shading and, oops, it moves my graph whenever I change it, the line itself. So it would be everything below and the line. So that's the only difference. The equals to versus the not equals to is points on the line versus not on the line. If you flipped it, like number 3, y is greater than x, now my shading, instead of being below the line, would be above the line. So that's like what's in red. So how do those solutions change to what was in blue? The solutions would change because now your answers come from above the line. And then for part 4, how would it change? Well, now the change is above and on. So we're really talking about the graphs and where the solutions come from. And again, you can shorten my definitions. You can write it all out. We are going to compare for the next few days and then some above, below, solid, and dashed. We're going to talk about our solutions. So in order to talk about our solutions, we need to know what that means. So what is a solution to an inequality? Just like in the warm-up activity where we had the points above, below, and on, a solution to an inequality is a point that you plug in that makes it true. So it's a point on the graph that makes, the inequality true. So what is a solution? It is a point on the graph that makes the inequality true. Okay. So what I want to do is graph the function like we know how. So ignore the inequality and start with your y-intercept. So the y-intercept is +4. So that means if you were to graph the equation y equals 2x plus 4, you would take the point, 0, 4, and then apply your slope. So the slope is 2x. That means you go up 2 over 1, up 2 over 1, so on and so forth, down to left 1, down to left 1, etc. The graph is greater than or equal to, therefore my line is solidly connecting them. Yes.
Does that mean if it's just like just less than or just more than dotted?
Yes. Yep. And then y values are greater than. So you look at the y-intercept and you decide, okay, from the y-intercept, are the y values bigger above or are the y values bigger below? So with respect to the y-intercept, where are the y values going to be greater? What? Above. Above. Therefore, we shade above the line. So you look at the y-intercept and you determine what makes that true. So then it says, what is a solution to this inequality? Guys, there are an infinite number of solutions. A solution is either in the red shaded region or on the blue line. So all of those points you plotted count. My red region is a little iffy to the board. So give me any point in this area, and that's a solution. Literally any number from that region is true. So you could say -4, 0. You could say -3, 3. I don't care as long as it's in there. Oh, really? What is a point that is a solution to the inequality given currently, but not a solution to y greater than 2x plus 4? So what would be the difference from what we currently have, which is greater than or equal to, versus greater than? What's the difference in the two equations? What do you think, Jesse?
Would it be like the equal to the inequality?
Yeah, it's the equal to and the inequality. That's the difference in the two equations. So where's the equal to and the inequality come from? It comes from the points on the line. Close. So the difference is, what is a point that is a solution to the inequality that is not a solution to that? Points on the line. The equal to makes the points on the line true. The not equal to makes the points on the line false. Oops. So technically my points on the line kind of like is this answer. And like number 2, it should have just been give me a point. So like you could have gave me 0, 4, etc. I was gonna say I already heard these girl. So I've kind of already hinted at this generalization, but I know we like precision. If a symbol is greater than or less than, the line will be dashed. If the symbol is greater than and equal to, or less than or equal to, my line will be solid. So it's starting to come back. You kind of remember doing this?
Yeah.
If the symbol is greater than or equal to, then we shade above. If the symbols are less than or equal to, then we shade
below. I'm having a deja vu.
Okay? So it's dotted or dashed, solid, above, below. Therefore, if you were going to make a graph of y greater than 2x plus 3 without even graphing it, you should be able to tell me that this graph will be shaded above. And my line will be, yeah, dashed or dotted. Either one is fine. I accept both. Some textbooks say dashed, some say dotted. Let's graph it. Y-intercept is at plus 3. My slope is 2. I really like slopes of 2 currently. It is dashed. And shaded above. Okay? Let's pick 3 points and determine if they work or don't work. So just like before, I'm going to pick a point above, below, and on. So for above, just to be funny, we'll do negative 4, 0. So if you plug that in, you get 0 is greater than 2 times negative 4 plus 3. So 0 is greater than negative 8 plus 3, which is negative 5. Is 0 greater than negative 5? Heck yeah, so that's true. It checks, so we're happy because it's in the shaded region. Let's pick a point on the line. So we'll pick, I always pick the y-intercept. It's the easiest point to know you're right about, right? 0,
Yeah.
3. So you pick 0, 3. So you get 3 is greater than 3. Is 3 bigger than 3? No, so that is false. So we're happy because it doesn't work. And we said it shouldn't work because my line is dashed. So we're like happy about that. And then a point not in the shaded region, which also should not work. Like we want this point to be false. Is 2, 0. And is 0 bigger than 7? No, it's false. We wanted it to be. It's outside or below the shaded region. So where I have X's and where I have checks match my graph. We are happy. Yes.
Why do we want these to be false?
Because this point right here in blue is on the line. My line is dashed. If the line is dashed, it means a point on the line is not a solution. So if I plug that point in and it's false, that means it's not a solution, which means it matches my graph. The green point's where no shading is. So the green point being false means it's not a solution, and that's what I graphed. That's why I said, like, I like to pick a point from each of the regions to help understand what do they mean. All right, so I need to check your phones. We're down to the nitty gritty. Your homework is the front of the next page. So keep going. You got to kind of go, yep.
Just the front.
Yes, 1 through 4, 2-8, graphing inequalities, day 1. Because you need to shade and then you have to pick test points and tell me about the slopes and the y-intercepts. So you're turning like an extra page in your notes packet. There's like a random blank page in there for some reason. Let me grab there. Let me turn this recording off and stuff.